work was referred to right at the very end by Antonio, which will be a theme of many talks to come. And his title is Stretching of Polydomain and Monodomain Nematic Elastomers, Experimental Study. Now, just before we start, there's a microphone, which, yes, if you could let me pin that, pin this on here. And if you put this into your pocket.
Okay.
Very good. Okay, thank you.
Okay, thank you. At first, I'd like to thank the organizers for kind invitations. So I'm talking about the nematic elastomers, but my talk is a totally experimental study. So basically, I'm a chemist. Okay, no mathematical formula in my presentations. So probably you feel uncomfortable, but be patient. Okay. Okay. So Antonio gave a nice introduction of this material, liquid crystal elastomer. This is a combination of elastomer and liquid crystals. And a unique feature of this material is a strong coupling of macroscopic shape and molecular orientation order. So today I will focus only on the nematic elastomers. So an important classification is a type of orientations, so the polydomain or monodomains. So as you know, a polydomain is composed of the randomly oriented domains. So they have no global nematic order, and the appearance is translucent. And the other one is a monodomain. They have a global nematic order, and the appearance is transparent. So if you want, the preparation of the polydomain nematic elastomer is easy. Okay? If you cross-link the mesogenic molecules in the high temperature isotopic phase or polydomain nematic phase, you obtain the polydomain nematic elastomers. But if you want monodomain nematic elastomers, you need some care for the alignment for the mesogenic molecule in the stage of cross-linking. So if you cross-link the mesogenic molecules in the nematic aligned state, you can obtain the monodomain nematic elastomers. Okay, so in my talks, I report some physical properties of polydomain and monodomain nematic elastomers. And the first topic is the polydomain nematic elastomers. We focus on the effect of cross-linking history on mechanical properties and nematic textures. So I will show you that the polydomain nematic elastomers show the soft or hard elasticity depending on the cross-linking history. For monodomain case, so we examine the effect of stretching directions on directed rotation and deformations. So I will show you that the monodomain nematic elastomers show the macroscopically uniform or non-uniform deformation depending on the stretching directions. So let me start from the polydomain case. Okay, so for the preparation of the polydomain nematic elastomers, we notice that we have two different routes. So one is the cross-linking in the high temperature isotopic state. And so you have the elastomers, but this material have a phase transition temperature. So if you cool the sample to the temperatures below the phase transition temperature, you obtain the polydomain nematic elastomer. We call this isotopic genesis polydomain nematic elastomers. The other one is directly obtained by the cross-linking in the low temperature polydomain nematic state. So we call this nematic genesis one. Okay. So we compare the several properties of these two types of elastomers. I show you that for some properties, so the genesis difference results in the big difference in the properties. And for some properties, there is no difference. Okay, so we compare the several properties. So one is the textures in the undeformed state, and also the dynamic linear viscoelasticity. And the third one is summary properties, but the experiment is still in progress. I don't talk about this one here. This one is a large deformation behavior, and polydomain monodomain transitions from the aspect of strength-strain relations and texture development. And this one is a response to electric field. Okay, this is a recipe of our sample. So basic reaction is this one. So monoacrylate mesogene and deacrylate Kress-Winkel. So this part is the dangling from the network backbones. Okay, so for our samples, the network backbone is consists of the CC bond. Okay, so we put this nematic mixture into this glass cell, and so mixtures involves the photoinitiator. So we irradiate the light, so reaction start. So macroscopic networks formed. So after reaction, we carefully remove these slide glasses. We have the freestanding films. So to obtain the elastomer with two different genesis, so we simply vary the temperature for cross-linking. So this, the phase transition temperature of this nematic mixture is around 50 degrees. So we use the two different temperatures for cross-linking. So this one corresponds to the isotropic state. This one corresponds to polydomain nematic state. So along this line, so we obtain the two types of elastomers. So firstly, we show the textures. Okay, this is the pictures by the polarizing optical microscope and the crossed nickels. You can see a marked difference. In the case of nematic genesis, we see typical Schlieren textures. Actually, so this texture is qualitatively similar to the Schlieren texture of nematic mixture before cross-linking. So this means the cross-linking effectively imprint the initial random director field in the elastomer matrix. And the other one, so this one, okay, is for the texture of isotropic genesis one, but it is composed of very small domains. At present, I don't know the domain size. Okay, and also so what determines the domain size? In this case, there is no memory for the director field. So this is also open questions. Okay, so this is a comparison of the dynamic linear viscoelasticity. Okay, linear means strain independent viscoelasticity. But in this case, we need an unusually very, very small amplitude to obtain this data. Because as I mentioned later, so in these materials, the director rotation is always accompanied by the imposed deformations. So we need an extremely small strain amplitude. So conventional rheometer is not available for this purpose. So this data is obtained by the collaboration with Dr. Mattenotti in Strasbourg. They have a special type of piezo-rheometer. So now strain amplitude is 10 to the minus 5. So this is 10 to the minus 3%. So this one is the storage modulus. This is the loss modulus. And this is the frequency. So you can see that there is almost no difference. Actually, this spectra is qualitatively similar to the conventional Labary polymer networks. Here is the Labary plateau. This is the transition regime. This is the Rouse type behavior. So it looks, the mesogene doesn't matter at all. Actually, so texture, so texture is very different, but there's no difference in the linear viscoelasticity. So personally, I really surprised this data. Okay, so I move to the large deformation behavior. Okay, so in this case, if you stretch the sample at a certain amount, you can induce transition to the monodomain state. Okay, so this experiment is already done in the 1980s. Okay, so but now we revisit these issues from the viewpoints of the effect of cross-linking history. So actually, prior to our experiments, Uchida did some simulations on the polydomain monodomain transitions with elastomers with two different genesis. So this is the simulation work. So he showed that in the case of isotropic genesis, so no external force is needed for transitions. So system is purely soft. Okay. But in the case of nematic genesis, so a finite stress needed for the transitions. So non-soft response. It is due to the memory of the initial directed field. It becomes a robust constraint for the directed rotations. So we did the corresponding experiments. So this is the data of isotopic genesis. This one is the data of nematic genesis. This is the stress, and this is the order parameter as a function of nominal strains. So in this case, order parameter is determined from the area of 100 micrometer square. So this area is much larger than the size of each individual domain. So in the undeformed state, order parameter is 0. Okay? So in the case of isotopic genesis, so up to 20%, okay, strain is very small, and not 0, but the strain is very small, and this is we have clearly plateau regions. But in these regions, order parameter steeply increases, and it reaches the constant values. It corresponds to the monodomain state. After these strains, the strain increases again. But in the case of nematic genesis, stress gradually increases with the strains. There is no plateau. And also in this case, we see a plateau of the order parameter, but in the monodomain state, the molecular order is almost similar. Okay. So to see the difference more clearly, this plot is more convenient. This is the orientation order parameter as a function of stress. So red data corresponds to the isotopic genesis. Blue one corresponds to the nematic genesis. So in the case of isotopic genesis, the order parameter steeply increase, almost discontinuously, order parameter jump from 0 to finite values. But in the case of nematic genesis, transitions occurs gradually over a wide range of the stress. Okay, but the final state, there is almost no difference in the order parameter. From this data, so we can estimate the mechanical work required for the transitions. Okay. So clearly, nematic genesis sample requires a larger mechanical work, about 10 times larger. Okay, so it's clearly shows that the initial random directed fields is a robust constraint for the directed rotations. And in contrast, in the isotopic genesis case, the sample is pure, very soft for directed rotations. So we also done the observation for the texture development during the transitions. So in this case, the optical axis of one polarizer is parallel to the stretching directions. So in the case of a high stretching, so the appearance becomes totally dark. But in the case of nematic genesis, you can see some remnant of the initial textures even at high stretch. Okay. So this remnant of the initial Schlieren textures is more clearly observed in this geometry. In this case, the stretching direction is have 45 degrees relative to the optical axis of crossed polarizers. So this corresponds to 50% stretch. This one is a 100% stretch. From viewpoint of the order parameter, this is assumed as monodomain, but you can clearly see the remnant of the initial Schlieren textures. But in the case of isotopic genesis, okay, texture is totally uniform. So the initial Schlieren textures cannot be eliminated by the high stretching. So this robust memory of the initial directed field is also confirmed by these pictures. Okay, this is a comparison of the textures before and after large deformations. So if you release the strain, so the sample recovers the original dimensions, but also the original initial textures also fully recovered. Actually, there is almost no difference. So actually, we know that some related theoretical studies, so by Uchida and Biggins and Wana, both of them will talk about this issue from the theoretical side. So I move to the response to electric field. So up now, so for liquid crystal elastomers, so electric actuations reported only for ferroelectric one. So they use electroclinic effect for actuations. Okay. So as far as I know, there is no report for electric actuation of non-ferroelectric liquid crystal elastomer. In this case, we have to use the directed rotation for actuations, but in the dry state, okay, so resistance for the directed rotation is very high, so we need an unrealistically high electric field, okay, for directed rotations. So final electrical deformation only reported for the swollen state, okay, gel state. But now, so we know the softness of the isotropic genesis polydomain. So we tried the electrical actuations for that samples. So the experiment is very simple. Some elastomer is put in this cell. The cell have so transparent electrodes. The point is that the gap of the electrode is larger than the film thickness. Okay? In this geometry, sample has no mechanical constraint from the rigid electrodes. We fill this cell with silicon oil. Okay, silicon oil is a non-solvent for this material, the optically transparent. Okay, and if we apply the electric field in this direction, AC electric field, these directions, so observing direction is parallel to the field directions. Okay, so I show you the movie for the electric actuations. This is a state without field, the observation under natural light. So sample is a polydomain, so there's strongly light scattering, so the appearance is totally black. Okay, the surrounding the silicon oil, this is transparent. So now we apply the electric fields normal to this screen. Okay, field frequency is 1 Hertz. Okay, so now the elastomer expands in the plane normal to the field axis. Okay. This also sample becomes transparent, so it indicates the directors oriented to the field directions. So now here we remove the field, so sample becomes the original dimensions. Okay, I repeat the movie. The sample shows the oscillating strain. So this frequency is a double of the field frequency. Okay. So this figure shows the strain as a function, electrical strain as a function of the field strength. And the blue data is for the isotropic genesis, and the green one is for the nematic genesis samples. So clearly, isotropic genesis sample shows a much larger electrical strain. So as a maximum, we observe the 35% strain at that field strength. This strain is much larger than the reported values for the ferroelectric liquid crystal elastomer. And also important point is we observe a threshold for the onset of the deformations. The threshold for nematic genesis sample is larger than that of the isotropic genesis one. So this is the intensity of the transmitted light as a function of the field strength. Again, so we see a threshold for the intensity change, but the importantly, this threshold value is the same as the threshold value of the deformations. So this indicates that the major origin of the deformation is directed rotation. But the puzzling point for us is the type of deformations. So you see that the sample expands in the plane normal to the field axis. This is totally opposite to our first expectation, because from the stretching experiment, our sample shows a positive coupling of the messaging orientation and the network backbone orientations. Okay, so they are parallel to each other. But in the electric field experiment, so it looks the coupling is negative, but so we have a contradiction. So I don't know why. Okay, so this is a summary of section of polydomain. So okay. So okay, I move to the result of the monodomains. Okay, so in this case, the sample is a monodomain. So if you stretch the sample, you can rotate the director to the stretching directions. So this experiment, this one is a very classical issue. And we know several experiments, but most of the experiments done in the 1990s. The very famous and interesting phenomenon of the formation of the stripe domains during the director rotation process. If you stretch the sample normal to the initial directors, so director can rotate in clockwise directions and anti-clockwise directions. So the sample have a coexistence of the domains of the directors of the angle plus minus theta. So sample shows some stripe domains. And this is reported by the group of Finkelman. But the group of Mitchell also did the same type of experiment using the different type of material. But they did not observe the stripe domains. And they observed the simple rotation of a single directors. Okay? So the situations seems very complicated. There are also, we know some theoretical studies for these issues, but they mainly focus on the formation of stripe domains. Quite recently, so we did this classical experiment using our samples. So personally, I wanted to see the stripe domains by my own eyes, but my students found a different type of phenomena. So I will show you that. Okay, the recipe of the sampling preparation is essentially the same as the case of the polydomains. So difference is only in the care of the alignment. So we use a wall effect to align the molecules. So glass substrate is coated by the uniaxially rubbed polyimide layer. Okay, so in this cell, these nematic mixtures form the planar alignment. So in this state, we irradiate right. So after that, so we remove the slide glasses. So we obtain the freestanding monodomain elastomer films. So we cut out the ribbon specimens from the sample sheet with various angles. Initial angle of the initial director relative to the long axis of the ribbon specimens. So long axis of the ribbon specimens correspond to the stretching axis. So 86 and 88 and 90s. Okay, so difference of angle is very small, but this small difference does matter. Okay. So now the dimension is like this. Okay, length is 5 millimeter. So width is 1 millimeter. Thickness is 24 micrometer. This is common to all three samples. So now here the sample is elongated from the both directions. So we observe the texture development, and also we measure the stress strain curve. Also, we use the infrared microscopy to characterize the messaging orientation distributions. So we use the stretching vibration of this group, cyano groups. This bond is parallel to the long axis of the messaging, so it can be used to characterize the messaging orientations. So we measure the absorbance of these vibrations. So the wavelength is here. Okay, so I will show you the firstly the result of the stretching at a slightly oblique angle to the initial director. Hi.
Can you tell us about how you hold the sample?
It's just clamped, mechanically clamped.
And something more? Is there freedom to rotate in this direction? To slide in this direction. So you stretch along the long axis?
Yeah.
And then in this direction, is there freedom to move or not?
No, not free, not free.
It's a very rigid
yeah,
frame.
it is a completely uniaxial stretching. Okay, this is a result of the result of 86 degrees. So now here the lambda x is the overall stretch. It is determined from the distance between the two clamps. Okay, so unity corresponds to the undeformed state. This is a 10% stretch. Okay, then the upper one is appearance under the polarized optical microscope using cross recall. Okay, so this is the appearance obtained by the natural light. So in this case, okay, the formation and the texture development is anyway, everything is uniform. So also we examine the orientation distribution by the infrared microscope. The area is 100 micrometer square. So this is the absorbance distributions. This intensity of the absorbance is proportional to the population of the mesogen. Okay. So here in undeformed state, the pattern is oval because the sample is a monodomain. Also this oval is slightly tilted, these directions, because so now the angle is 86. So if you stretch the sample, this pattern is tilted in the initially biased directions. But the point is that the shape of the anisotropy is almost constant during the deformations. This means the director simply rotates to the initially biased directions. Okay. So this figure shows the rotation angle of director as a function of overall stretch. So it looks around 70% stretch. The director rotation is completed. This is a strain curve, and obtained in the equilibrium state at each strain. You can see that during the director rotations, we see some the plateau regions. The height is 20 kilopascal. After the director rotation, after the completion of the director rotation, stress increases again. So actually, these data are successfully explained by the semi-soft elasticity theory by the group of Warner. So I don't enter into the details of the theory, but this solid line is a result of fitting. So anyway, in the case of uniform process of director rotations, the theory does work. And so the next is the case of the stretching at nearly 90 degrees to the initial director. So in this case, the process becomes macroscopically non-uniform. Okay, this one is undeformed state, but in the case of 30% stretch, we see a formation of necking. So in this case, the necking occurs at the two places. Okay. This also the samples became opaque. Okay. If you stretch further, so the necking propagates, and finally, this is in the case of 100% stretch, the sample becomes totally uniform, totally transparent. But anyway, the process is deformation, and also the process of director rotation. Both of it becomes non-uniform. This is the result of the case of 90 degrees. Also, we observe the necking formations. In this case, necking formations occurs at one place here, but you can see that sample becomes became opaque. And the other feature is essentially similar of the to the result is a case of 88 degrees. So interestingly, so if you release the strain after necking deformations, the sample recovers the original shape fully. So it is very interesting because in the case of usual necking for a semi-crystalline polymer and glassy polymers, so after necking deformations, if you release the samples, if you release the strains show the large residual strains because the plastic flows is always accompanied by the necking deformation. But in this case, the sample is elastomer, so it recovers the original shape completely. But in this case, the sample undergoes the necking deformations. So for more detailed characterization of this necking phenomena, so we use the infrared microscope. So now we select the 5 different positions from A to E. So each area is a 100 micrometer square. Okay, so this is the undeformed state. Of course, this orientation is uniform. Okay. Okay, this is the result in the case of 30% stretch. So now you can see a steep gradient of the degree of director rotations from the position A to E. Okay, at position A, so full rotation of director already occurs. Okay, but the position E looks like nothing happened. So position D, director still stays in the initial state, but the anisotropy becomes smaller. On the position B, the director rotates the stretching direction, but the anisotropy is smaller than A. And the position C, the distribution looks almost isotropic. And this is the data of the 50% stretch. So now in the position P, director rotation is completed. And so now here at the position E, the pattern becomes isotropic. So in the case of 100% stretch, so now at all the positions, so director rotation is completed. So in this case, the pattern of the absorbance changes like this. Okay? The total and also appearance initially transparent. On the way of the director rotation, sample becomes opaque. Then finally, sample becomes transparent in the monodomain state. So how can we explain that? At first, we use the simple two-state models for the explanations. Okay, so we simply simulate the absorbance patterns using this idea. So now the idea is very simple. Okay, so now the sample have a coexistence of the two states, plus theta and minus theta. For these simulations, we use the initial pattern, okay, in the undeformed state. So simulation tells us that we should have the appreciable bumps at 4 corners and in the patterns on the way of the director rotation. But in the experiment, we see no appreciable bumps. So I think this explanation doesn't work. So anyway, the features of the observation is almost isotropic patterns appears, and also the opaque and also appearance becomes opaque. So these two features are qualitatively similar to the familiar polydomain structures composed of a random director field. So now we expect that a kind of polydomain structure is formed in the observational area, so 100 micrometer square. So definitely we need an observation with higher resolutions, but this is a next issue of our studies. Okay, we also examine the position dependence of lateral strain, macroscopic lateral strain, as a function over all stretch at each positions. Okay. Of course, in the necked portions, the formations proceeds faster than that in unnecked portions. But the important point is that so directed rotation at each point completes at the, this characteristics value of lateral strain around 0.67. And this green data is the data of the uniform process. So this means that the local strain required for the full rotation director is the same. Okay? And also this characteristic strain is independent of the whether deformation is uniform or non-uniform. Also, we have to, so anyway, so necking deformation requires local softening. Okay, so next we consider the origin of the local softening for nematic elastomers. So in the experiments, we noticed that so necking often starts at the portion near the clamps. This is not usual because in the case of conventional familiar necking phenomena, so necking usually starts around the central positions because as the edge part, this is affected by the boundary conditions of the clamps. So that edge portions should have the least transverse constructions. But in the central positions, should be subjected to large transverse constructions. So from this point, so we think that the origin of the local softening is different. So nematic elastomer is different from that in the conventional necking phenomena. This is my guess. So if small but finite fluctuation of initial director exists in the sample, so I think some portions can select the director rotation via semi-soft mode. It may result in the local softening. So I think such fluctuation may be caused by some heterogeneity of samples. But I have no evidence of that. So and also we have to consider this problem. So what determines the types of instability? So we observe the necking deformations. But at present, we did not observe the stripe domains. But now we have many parameters. So for example, aspect ratio and the width and thickness ratio and chemical structure and the cross-link concentration, temperature and the fabrication method of monodomain, etc. So the situation looks very complicated. So finally, so I will show you one example for this complexity. So this is the preliminary, the data of the preliminary experiments. So sample is thicker sample. So now the angle is 90 degrees. Difference is only in the thickness. So in this case, the sample shows no necking deformation. No necking deformation. But the directed rotation process is non-uniform. So you can see we see macroscopically the coexistence of the transparent and the opaque regions. And so even at the high magnifications, we don't see the stripe domains in these opaque regions. So anyway, phenomena looks complicated. Okay, so this is the summary of the section of the monodomain. So I stop here. Okay. Thank you.
Thank you for an interesting talk with huge mysteries. Very much. Thank you very much. Questions?
So,
just want to make sure I understand the boundary conditions at the edge. If I looked at your sample where it formed the neck, it looked like the attachment to the edge was slightly smaller than the attachment at the other edge. In other words,
you mean we have initially...
yeah, I mean, so do you fix it so that the vertical length is the same at both ends throughout the experiment?
Yeah, should be similar.
Should be similar, because if you just look at it, it looks like this one's a little thinner. Yeah. Yeah. So I mean, it's maybe maybe it's an optical illusion.
This one.
Yeah, that one or the next one I think showed it more, right? So at this point, maybe it's an optical illusion.
So you mean this?
Yeah,
So this
right.
one, this one.
So in the region where you have the slope at the left end, that would be the region where you would have to have something to accommodate the change in height.
Mm.
Okay, one final question. So if you take this and just turn it around, would you always get if you were to attach the left end to the right and stretched it, you would presumably get the necking at the right end?
Yes.
Which would be an inhomogeneous
Yeah.
sample.
Actually, we repeated the same type of experiment using a different sample. If the angle is the same, we always see the necking deformation.
But always on the same side of the
Yes,
sample.
sir. Yeah, but if the sample is different, the onset position is different. Yeah, but anyway, the angle does matter.
Peter, question.
How flat is the sample?
How flat?
Yeah.
So actually, we measure the thickness of some several positions, but no appreciable difference in the thickness.
I mean, does it perhaps arch like this when you're going across?
Sample have some gradient of the thickness.
No.
No.
That the sample somehow develops a kind of an arch as you're moving along. That the middle is higher up, more out of the plane than the edges.
So you mean the sample have some bend?
In the transverse
The
direction.
transverse direction.
Thickening of the sample or something.
I don't think so, but because anyway, so we use the same conditions for the different samples, okay? But in the case of 86 degrees, okay, sample undergoes the uniform deformations. If I say such bend it doesn't matter, I think, and the result is different from sample to samples. Okay.
I was really thrilled by your presentation in the sense that at some point I thought you were getting closer to destroying completely my credibility by saying stripes do not exist. And so, no, thank you very much. As usual, it's a privilege to be working as a theoretician in a field where you do this kind of beautiful experiments. Now, the necking and the question that was just raised. So I often get asked the question, similarities with respect to wrinkling in thin sheets be under tension. And in that experiment, wrinkling is a compressional instability that starts because when you stretch close to the clamps, you generate compression and oscillations out of the plane of the kind that Peter was mentioning. And this phenomenon is very thickness dependent somehow. So since you get also thickness dependent, I was wondering whether this could be somehow a hint for your experiments as well.
Okay. You mean that I think the final slide, so I will show the thickness dependence of the phenomena, but I think the wrinkling is related to the...
This phenomenon here. Okay, mine doesn't work very well, but okay. Maybe I should stretch. Okay, it's this phenomenon here. And if you did that in a thin sheet, the critical region for the onset of the instability would be regions near the clamps, not in the middle, but near.
Another question here.
I have a question on the first part of your talk about the polydomain. So you did cross-linking on the isotropic state and the cross-linking on the nematic state. And the question is, the different results are, in your opinion, related with the sides of the polydomain domain? And the second is, if you think that this is the answer, is it possible from the chemical point of view to build a material who has an intermediate size, so to see if there is a kind of transition between the two behaviors?
So the first point, I think, so anyway, but in the case of isotropic genesis, okay, the size of the domain is very small, okay, but we don't know the size. So we cannot control the size. But so open question is what determines the size of the domains in the case of isotropic genesis. What is the second question? I forgot that.
No,
It's okay. It's okay.
There's a way to control the size, and
Ah.
you can make like intermediate size
Ah.
between the completely isotropic and the complete nematic to see if.
So in the case of nematic genesis, we may control the domain size because it depends on the defects, so that we may control the number of defects, so we can control the size of domains.
In your second part of your talk, you have an anomalous response of shape to electric field. So how important is this surface effect? Do you have any idea?
Yeah, actually, so we did several experiments using spacemen with different thickness. Okay. Actually, we use a sample with, I think, twice thicker samples, but the phenomenon is the same. But actually, the 1 millimeter side and several millimeter side experiment is not possible because we need a unusually high electric field. Okay.
Could I make a comment about this? This electric field result, to my way of thinking, is completely inexplicable. I've tried for 2 or 3 years, and there are others in the audience who've tried with me. If you take an isotropic elastomer and let it float between the electrodes, then applying a field, it should get thicker and thinner and smaller in the plane. So an isotropic elastomer would have the opposite reaction, the one that Kenji's got. And also, as he points out, the mechanical stretching experiments point to a prolate elastomer, which also should get thicker as you turn on the electric field. So in every regard, I find this an extremely difficult and challenging result, which I've certainly failed to explain over several years. I'm not sure that everybody in the audience is actually aware just how anomalous and strange this result is.
The dielectric anisotropy is positive?
It doesn't matter whether it's positive or negative. It should always get thicker, and therefore thinner in the plane. The oil is not miscible with the rubber, is it? Everything we've reached for to try and explain this, we've failed completely. So, on that happy note, perhaps we can thank the speaker once more.